We want to talk about complex matrices, especially the complex counterpart of symmetric matrices, which are Hermitian symmetric, and orthogonal matrices, which are unitary matrices. So complex matrices. Most of this lecture is about on definitions and short proofs. So a real matrix has real coefficients but the eigenvalues can be complex. The eigenvalues can be complex. The space Cn, it's a space Cn, vector space Cn of vectors with n components. Addition, multiplication follow the same rules. Addition, multiplication follow the same rules. However, length is computed differently. For example, 1 plus iota, this is 1 square, this one, plus iota square. So if you recall the norms that we talked about in chapter 3, this is simply the same definition. So this is 1 square, is 1 plus iota, the magnitude of iota is 1, so again this is 1 and this is 2. Instead of 1 square plus iota square, which is 1 minus 1, which is 0. So this implies x norm square is actually x1, the first element of x, plus x2 square, plus so on and so forth, plus xn magnitude square. This is the nth element of x. So we need to define, need to modify definitions of inner product, transpose, symmetric or Hermitian matrix, and orthogonal or unitary matrix. So every symmetric matrix, just like we saw for the real symmetric matrix, so every symmetric or Hermitian matrix has real eigenvalues, and we'll prove this in a little while. And moreover, their eigenvectors, so this is the most most important property of symmetric matrix. Moreover, their eigenvectors can be chosen to be orthonormal, and this is irrespective of whether or not the eigenvalues are distinct, whether or not the eigenvalues values are distinct. This implies a full set of eigenvectors exist. A full set of eigenvectors exists, which implies matrix, or maybe symmetric or Hermitian matrix, implies symmetric or Hermitian matrix. Hermitian matrix is always diagonalizable. It's always diagonalizable. So let me give you a complex number overview. So this is the real part. This is the complex J imaginary part. This is a vector R, length is R, theta. This is theta here from the real axis. This is R E J theta, which is A plus JB. This is R E minus J theta, which is A minus JB. So these two are conjugates. Conjugates mean plus is replaced by minus, where A is R cosine theta and B is R sine theta. Okay. And R squared is, by Pythagoras theorem, A squared plus B squared, or magnitude of R is simply A squared plus B squared, and theta is tangent inverse B over A. Where sometimes we'll write J, sometimes we'll write iota, or J is under root minus the square root of unity. And this is the mirror image across the real. So conjugates are mirror images. Is a mirror conjugate are mirror images across the real axis. And probably you already know that A plus JB into C plus JD multiplication is AC plus J square, which is minus BD plus J into AD plus BC. And so this is multiplication. And addition is like this. You add the real part and add the corresponding imaginary part. So A plus JB plus C plus JD is simply A plus C plus J into B plus B. And finally, A plus JB conjugate. So this one is conjugate is simply A minus JB. So plus changes to minus. That's the only change that happens. Nothing happens to the real part, nothing that happens to the value of the imaginary part. So conjugate reverses the sign of imaginary part. The sign of imaginary part. So Okay. So let's look at brief some more facts. Conjugate of a product, conjugate of a product equals product of conjugates, equals product of conjugates. This means A plus JB into C plus JD. When I conjugate it, this is simply, so inside I have from here, this is AC minus BD, and since I conjugate this will become minus J into AD plus BC. But this is what? This is simply A minus JB into C minus JD, because when you multiply, this is AC minus and minus plus, then minus BD, then this is minus JAD minus JBC, which is A plus JB conjugate into C plus JD conjugate. So the conjugate of a product, so this is the product, and the conjugate here is simply the product of the conjugates. Okay, the second one is conjugate of a sum, conjugate of a sum equals sum of conjugates, sum of conjugates. So A plus B, A plus JB, A plus JB plus C plus JD. If I do the conjugate here, so A plus JB plus C plus JD here, so this one, so this is simply equal to A plus C minus J into B plus D, but this I can write as A plus JB whole conjugate plus C plus JD whole conjugate. So the sum of the conjugates is simply conjugate of a sum is simply the sum of the conjugates. And finally, multiplying A plus JB by its conjugate A minus JB produces a real number, R square, which is A square plus B square. And we can see that A plus JB into A minus JB equals A into A is A square, plus JBA minus JBA cancels, and plus into minus is minus, J square is minus, so this plus B square, which is R square. And this where R is the absolute value, this is not the rank, is the absolute value of A plus JB, and this is equal to A square plus B square. Okay, and we also saw A is equal to R cosine theta, B is equal to R sine theta, where A plus JB equals R cosine theta plus J sine theta. This is Euler's identity, so this is R E J theta. This is Euler's identity. So this is the polar form. This is the polar form of the complex number. This is the rectangular form or the Cartesian form of the complex number. So complex vector X can be written as complex vector X is x1, x2, xn with xi equals ai plus jb, maybe ibj, or yeah, x is ai plus b. Okay. So vectors v1 to vk, v1 to vk, so this set of vectors are not independent, are not independent if some non-trivial combination gives, if some not, this is exactly the same definition, if some non-trivial combination gives C1 V1 plus C2 V2 plus so on plus CK Vk equals 0, where Cj may be complex. And we already saw the norm of the vector is, so the length or norm, Euclidean norm of x is x maybe x squared, Euclidean norm squared, so length squared. So length squared or Euclidean norm of the vector is Euclidean norm squared actually. Euclidean norm squared is x1 squared absolute value plus absolute value here, or just as we have seen before, so y equals some vector 2 plus 4j and 2 minus j. This implies y norm squared is 2 plus 4j magnitude square plus 2 minus j magnitude square. This is 4 plus 4 square 16, or maybe I write it like this, 2 square plus 4 square plus 2 square plus 1 square. So this is 4 plus 16 plus 4 plus 1, 16 for 20, 24. This is 25, or this implies the length of the vector is 5. So if you have two complex vectors, how do we define the inner product? So for complex vectors x and y, x dot y equals x. So this is how you define the inner product, x h y. What is x h y? This is x conjugate transpose y, where h is conjugate and transpose. As maybe I write conjugate, h is conjugate, and transpose. Okay. So this becomes then x1 conjugate y1 plus x2 conjugate y2 plus so on plus xn conjugate yn. Now we know from the inner product definition of in the third chapter, x dot y, chapter 3, x dot y is equal to y dot x for real x y. This doesn't hold when x y are complex. meaning. So what happens for the complex one? So what is YHX? So YHX is maybe Y dot X. So from here, Y dot X is YHX, which is equal to Y1 conjugate X1 plus Y2 conjugate X2 plus so on and so forth plus YN conjugate Xn, and this is simply equal to XH Y whole conjugate. If you do that, actually you will get X conjugate Y1. So this is X conjugate Y1, X conjugate. So if you conjugate the whole thing, this is equal to 1. So that is why this definition does not hold when X and Y. So does not hold when X and Y are complex. So X dot Y is XHY and Y dot X is XHY conjugate. So just be careful, you can't use it as in the same way as for real vectors. This is the major difference here. A conjugate transpose is called A Hermitian or A Hermitian IJ, the ijth element actually. The ijth element here is simply A conjugate Ji. So if we have this matrix 2 plus I, 4 minus I, 0, 3I, 5, 0, and I do Hermitian, which is the conjugate transpose. This means I do 2 plus I, 3I here, then I do 4 minus I, 5 here, 0 here, 0 here. This is the transpose. And when I do conjugate, so conjugate, this becomes a minus, this becomes a plus, and this becomes a minus. So when you do H, which is conjugate transpose, either do conjugate first or transpose first, this will make a difference. So this is what you get when you do transpose and then you do conjugate. Okay, so inner product, I think I have a cold. So inner product of X and Y is XHY, where so this is the general definition. So if X is real, there is no use of conjugate, this is simply transpose Y. So where orthogonal vectors have X, H, Y equals 0. So this is a scalar, this is not a vector, this is a scalar, so it's dot product, this is 0. So squared length, I know I'm repeating, but in any case, squared length of X is the norm squared, which is XH, and this is x1 magnitude square, x2 magnitude square, and goes on for xn magnitude square. Also, AB transpose equals B transpose A transpose. This implies AB Hermitian equals B Hermitian A Hermitian, which is equal to B conjugate transpose A conjugate transpose. Okay. What about Hermitian matrices? So Hermitian matrices. These are the counterpart of symmetric matrices. So counterpart of real symmetric matrix. So whatever is true for real symmetric matrix is also true for Hermitian matrix. So these are the supersets. This is a subset. So if A is equal to 2, 3 minus 3i, 3 plus 3i, and 5. So this implies AH equals, so when I do when I do transpose, this is 2 and 3 minus 3i, this is 3 plus 3i, this is 5. So elements on the main diagonals don't, so whenever you do transpose, the elements on the main diagonal, they just are anchored there. So when I do the conjugate, this becomes plus and this becomes minus, and this is exactly the same as A. So for Hermitian symmetric matrix, this implies A equals A Hermitian transpose. Okay, and what are the properties? So diagonal elements, so these must be real. So diagonal elements must be real, as Aij equals A conjugate Ji. Okay, so what are the properties here? So if A equals A Hermitian, then for a complex X, for a complex vector X, XH AX is a real number. This is, by the way, called the quadratic form, is a real number. This, by the way, is called the quadratic form. So you can learn more about quadratic forms in chapter 6. So X Hermitian AX, if it's a real number, if I take the conjugate of this one, I should get the same number. So if I take the conjugate transpose here, this will become, so order reverses, XH AH, and XHH would be X. This is equal to XH A XY, because A equals AH, and this is exactly the same as the conjugate of the number. So this is same as the number. So this implies if the number and you do conjugate or conjugate transpose, this is equal to the number, this implies number is real. The second property, which is the most important property, is if A is equal to AH, then every eigenvalue is real. Every eigenvectors can be complex, but every eigenvalue is real. And how you prove that? So AX equals lambda X, or if I multiply XH here, I multiply XH here. So multiply XH here, so I get XH times AX equals lambda norm squared, and now this is real. This is real and positive because X is not equal to 0. This implies lambda is real. And we can look at an example. So A minus lambda I, maybe the same matrix. So A minus lambda I equals 2 minus lambda, 3 minus 3 iota, 3 plus 3 iota, 5 minus lambda. So this implies 2 minus lambda into 5 minus lambda, 5 minus lambda. This is the conjugate, so this is minus 3 minus 3 iota into 3 plus 3 iota. So this is equal to, and this is equal to 0. So this is equal to 5 to 10 plus lambda square minus 5 lambda minus 2 lambda minus 7 lambda, and this is minus square of this one, 3 square plus 3 square. So this is equal to lambda square minus 7 lambda, and this is 9 plus 9, 18 minus 8, or this is equal to 0. So this implies lambda minus 8 into lambda plus 1 equals 0, or lambda 1 equals 8 and lambda 2 equals minus 1. So if we check from the trace value, so 8 minus 1 is 7, so 2 plus 5 is 7. So it's actually this matrix. So 2 plus 5, so the trace is 7. So these eigenvalues are all right, and these are also real. So 8 and minus 1. And then two eigenvectors of a real symmetric matrix, or a Hermitian matrix, if they come from different eigenvalues, which means distinct from different eigenvalues, are orthogonal to each other. If the matrix is not symmetric, then we have two different eigenvectors, but they are not necessarily orthogonal. So the proof here is Ax equals lambda 1x and Ay equals lambda 2y and A equals AH. Okay, so if I do lambda 1x Hermitian with y, this should be equal to Ax Hermitian y. This is the eigenvalue equation, and this is equal to x Hermitian Ay, which is equal to, because x Hermitian A Hermitian y, but this is equal to x Hermitian A Hermitian y, but this is equal to x Hermitian Ay because of because it's a Hermitian matrix, and this is equal to x Hermitian lambda 2y, or this is equal to lambda 2 x Hermitian y. Okay, or this implies lambda 1, because these are real, so when we do conjugate, it's not going to affect this one, and this is scalar, so no need of taking transpose. So lambda 1 x hy equals lambda 2 x hy. So since lambda 1 is not equal to lambda 2, this implies x hy has to be equal to 0, or this implies x is orthogonal to y. And we can do a quick example here. So the example is, let's find the eigenvectors corresponding to for the same matrix. So A is 2, 3 minus 3 iota, 3 plus 3 iota, and this is 5. So if lambda 1 is equal to 8, so we had 8 and minus 1. So if lambda 1 is equal to 8, this implies A minus lambda 1I equals 2 minus 8 is minus 6. This is 3 minus 3 iota. This is 3 plus 3 iota, and 5 minus 8 is minus 3. And if I do the same thing, if A minus lambda 1I into x1 equals 0, this implies minus 6, 3 minus 3i, 3 plus 3i, minus 3 into alpha beta equals 0 vector. And if I solve this one, so this implies minus 6 alpha plus 3 beta minus 3 iota beta equals 0, or alpha equals and for the second equation, and 3 plus 3 iota into alpha minus 3 beta equals 0. So from this equation, I think from this one, I have beta is equal to 1 plus iota into alpha. So if I pick alpha equals 1, so if alpha equals 1, this implies beta is equal to 1 plus iota. So x1 equals 1 and 1 plus iota, and for the second eigenvalue, and a minus lambda 2I into x2 equals 0 implies this lambda is minus 1, this lambda was 8. So 2 minus 1, 2 minus plus 1 is 3, 3 minus 3 iota, and this is 3 plus 3 iota. So 5 plus 1, 6 alpha beta equals 0. So this implies 3 alpha plus 3 minus 3 iota into beta equals 0. So from here we can see alpha is equal to if alpha is equal to minus 1, alpha is equal to minus 1 plus 3 iota into beta. Oh, sorry, minus 1 plus iota. Minus 1 plus iota into beta is too far away. Minus 1 plus, so goes on this side, this is minus 1, this plus, so plus iota into beta. Or if beta is equal to minus 1, this implies alpha is equal to 1 minus iota. So x2 or x2 equals 1 minus iota and minus 1. So check x1 Hermitian into x2. This is equal to 1. This one conjugate doesn't make a difference, into 1 minus iota plus this conjugate 1 plus I conjugate into minus 1. So this is equal to 1 minus iota plus, or this minus 1, this minus 1 here, and this is 1 minus iota, so this is equal to 0. So x1 is actually orthogonal to x2. Okay. So this implies when A equals AH, this implies diagonalizing matrix can be chosen with orthonormal columns. Again, this holds even for symmetric matrices. This holds even if the eigenvalue is repeating. So a real symmetric matrix, because it holds for a real symmetric matrix too. A real symmetric matrix can be factored into A equals, so that was S lambda S inverse, or this is equal to Q lambda Q transpose, where Q equals S. So Q has what? So this is a matrix of independent matrix of independent eigenvectors, and this is the matrix of orthonormal eigenvectors. Obviously, these are also independent. Okay, and this lambda is a diagonal matrix of eigenvalues. Diagonal matrix of eigenvalues. corresponding eigenvalues. Remember, these eigenvalues and eigenvectors have to be corresponding. If lambda 1 is the first one, then the x1, the corresponding eigenvector x1, has to be the first vector in the matrix. Okay, so this means A, which is equal to Q gamma lambda Q transpose, is simply maybe I call these E1 now. Let me call them E1. So E1, En. So these are orthonormal eigenvectors. These are orthonormal eigenvectors. These are actually Xi. These are Ei. This is lambda 1 goes up to lambda n, and then I have E1 Hermitian or E1 transpose and this goes up to En transpose. When I multiply this out, this will become lambda 1 E1 into E1 transpose plus lambda 2 into E2 transpose plus lambda n into En transpose. And what are these? These are symmetric matrices of rank 1, because this is a column times a row of rank 1, and this A is, by the way, symmetric. Okay, and this theorem is called the spectral decomposition. This is called the spectral decomposition of a matrix. Spectral decomposition of a matrix. And if I order these eigenvalues in descending order, such that lambda 1 is greater than lambda 2 is greater than lambda 3, and so on and so forth. And then if I apply a threshold, and I say all eigenvalues less than lambda k are very small and can be neglected, so my order of the matrix reduces from an n by n to k minus 1 by k minus, or if I reject everything above k, less than lambda k, so this will change from an n by n matrix to a k by k matrix. And this is what is done when you call these vectors feature vectors in artificial intelligence, in machine learning. Then this is actually, you are reducing the feature set. Yeah, so this is how you actually reduce the number of features when you apply the same concept into machine learning problems. Okay, so let's look at an example. The same matrix that we did before: 2 minus 1 minus 1 2. The eigenvalues were, I think, 3 and 1, so implies eigenvalue is 3 and eigenvalue 2 is 1, because 2 plus 2 is 4, 3 plus 1 is 4. The determinant of this one is 4 minus 1, which is 3. Determinant of this one is 3. And what were the eigenvectors? And recall x1 was 1 minus 1 plus 1, and x2 was plus 1 plus 1 plus 1 plus 1. But the problem here is these are orthogonal, so x1 dot x2 is 0. However, x1 norm squared is not equal to 1. So what I can do is I can actually divide x1 by x1 norm. If I do that, I get E1. And what is the length of x1? Where this length is 1 minus 1 squared plus 1 squared under root. This is under root 2. So this one is 1 over under root 2 minus 1 plus 1. Now this length is 1. The norm of E1 is 1. And similarly, E2 is x2. Otherwise, you have to use the Gram-Schmidt to get the orthogonal vectors. You can't write it like this, where x2 norm is the same. So this is square 1 square plus 1 square, which is equal to under root 2. So E2 is also 1 over under root 2, 1, 1. Again, the length here is now 1. And I can write this A, or A equals half E1, sorry, A equals 3 times E1 transpose plus 1 times E2 transpose, which is equal to 3 into E1 is 1 over root 2 minus 1 over root 2 plus 1 over root 2 into minus 1 over root 2, 1 over root 2 plus 1. This is 1 over root 2, 1 over root 2. Even if these vectors are not the same as before, but you can always multiply. Maybe before we calculated was minus 1 here, plus 1 here, but in any case, it doesn't make a difference. You can always multiply by a scalar and the eigenvector is still the same. And you can always check whether this is an eigenvector or not. So the check for the eigenvector is, check this thing, A minus lambda I into xi, is this equal to 0 or not? So this is the check. This is the check for the eigenvector. If the eigenvector satisfies this equation, obviously this is 0. So this is 1 over root 2, 1 over root 2. And if I multiply this out, this would become rank 1 matrix. And these are projection matrices. So minus into minus is plus, half is 3 over 2. This one is, so 3 multiplied with all the entries. So this is minus into minus, this is minus 3 over 2. This is minus 3 over 2. This is plus 3 over 2. This is half. This is half. This is half. This is half. If I add them up, I should get A. So 3 by 2 plus half is 4 over 2. 4 over 2 is 2. Minus 3 by 2 plus half minus 2 over 2 is minus 1. This is symmetric matrix. It has to be same here. And then 3 by 2 plus this one, 4 over 2, and this is 2. This is the same as before. So these two are all right. And obviously these eigenvectors are also the same. Okay. So if A is real, and its eigenvalues are real, this implies eigenvectors are also real. So remember, if you recall, for the rotation matrix, the eigenvalues were complex, so that's why the eigenvectors weren't real. And if A is real, then all, and this is the case that I just talked about, then all complex eigenvalues come in conjugate pairs. And what is the proof? So proof is, if Ax equals lambda x and Ax conjugate equals some lambda bar, or lambda bar is same as lambda conjugate into x conjugate. Okay. So if A plus JB is an eigenvalue of a real matrix, then A minus JB is also an eigenvalue, of the same matrix, same matrix. Okay, so this is all we want to talk about the Hermitian matrices. So let's look at the counterpart of orthogonal matrices, which are the unitary matrices. So what are unitary matrices? Remember, the orthogonal matrices are square matrices that have orthonormal, is called a unitary matrix, is called a unitary matrix such that U equals I equals UH equals I, or U inverse is simply UH. Just like an orthogonal matrix preserves the length and the inner product, same is the case for the unitary matrices. So multiplication by U has no effect on inner products, angles and lengths, or lengths, or this implies UXH into UY is simply XH UH UY. This, by the way, is identity, so this is XHY. Also UX norm square equals UXH into UX, which is equal to XHU. So this is equal to XH UH U into X. This is again identity, so this is X norm squared. So your length is preserved. Eigenvalue, so maybe this is property, so this is the first property we want to look at. The second property is every eigenvalue. So every eigenvalue of U has absolute value equals to 1. That is, this implies lambda is 1. So let's see. So U times X is some lambda X, and what is lambda X norm? This is simply absolute of norm from chapter 3, and this is X norm. So absolute value here in X norm. Also UX equals X norm. This is from here. UX equals X norm from here. So this implies lambda from here and here. When you combine them, this implies lambda, absolute value of lambda is equal to 1. Okay. So eigenvectors corresponding to different eigenvalues are orthonormal. So this is the same case for the symmetric matrix. So let UX equal lambda 1 X and UY equal lambda 2 Y, where lambda Y is not equal to lambda 2. So if I do XHY, this is simply equal to UXH into UY, because the length of X is not being changed, and this is equal to lambda 1 X H into lambda 2 Y, and since lambdas this is equal to lambda 1 H lambda 2 into X H Y, or so either lambda 1h into lambda 2 should be just conjugate here. Maybe I just put a conjugate here. It doesn't make sense. So conjugate here. So lambda 1 conjugate into lambda 2 is equal to 1, or x h y equals 0. However, lambda 1 h into lambda 1 conjugate into lambda 1 is 1, but lambda 1 conjugate into lambda 2 is not equal to 1. So this implies x h y equals 0, or eigenvectors are orthogonal and obviously orthonormal. So let's compute the eigenvalues of a unitary matrix. So the eigenvalues of a unitary matrix are, so example, U equals sine t minus cosine t sine t. This is the same matrix that we computed last time. So cosine of t minus sine of t, sine of t, and cosine of t. So if I compute the eigenvalues, so u minus lambda I magnitude is cosine t minus lambda, and this whole squared, minus plus minus plus sine squared t. So if I expand this one, this will be lambda squared minus 2 times lambda times cosine of t plus cosine square t plus sine square t, which is equal to 1. So if I compute the eigenvalues, so lambda 1 comma 2 using the quadratic formula is cosine of t plus minus under root square of this one. This is 4 cosine square t minus 4 divided by or maybe this was 2 here, 2 divided by 2. So this 2 cancels with this 2, this 4 comes out, becomes a 2, and this cancels. So I can write this as cosine of t plus minus under root cosine square t minus 1, which is equal to cosine of t plus minus j. If I take out minus 1 here, this is 1 minus cosine square of t, which is sine squared sine t. So this is cosine of t plus minus j sine of t, which is, by the way, e plus minus j t, and this is equal to this because of Euler's identity. When you study signal and system, you'll be using this Euler's identity over and over again. Also, in signal and system, you'll be studying the Fourier transform. So if I'm ever going to prove this one, this is the Fourier matrix. Sometimes this n is capital, sometimes this n is, since we've been using it small, so this is small. This is 1, and this is also 1. This is goes here, this is 1. This is, maybe I write 1 over here too. 1, this is w. This goes here, this is w n minus 1. Comes down, this is w n minus 1. So it's a symmetric matrix. Goes here, this is w n minus 1 squared, where w is ej 2 pi by n, and this is the Fourier matrix. Divided by under root e. So in some cases you use under root n, in some cases you don't. This, by the way, is pi. And to find inverse Fourier transform, to find inverse Fourier simply replace W. This is called the twiddle factor, by the way. This is the twiddle factor. This is the twiddle factor. W by W minus 1. So then there's a skew symmetric, and the counterpart of the skew symmetric is a skew Hermitian. So skew Hermitian matrix satisfies. So skew Hermitian matrix satisfies KH equals minus K. So if A is equal to AH, this implies K equals JA, because K Hermitian is simply J conjugate A Hermitian, which is equal to minus J A, which is equal to minus K, because A equals AH and J conjugate equals minus J. So eigenvalues. Since the eigenvalues of a skew symmetric matrix are real, so because of this J, the eigenvalues of a skew Hermitian matrix are purely imaginary. Are purely imaginary. Eigenvectors, though, are unchanged. Eigenvectors are unchanged. So let me just quickly do an example for the unitary for the skew symmetric matrix. So K is equal to IA, or this is equal to JA. Does means the same thing, and this is 2I, 3 plus 3I. This is 3 minus. This is minus 3 plus 3I, minus 3 plus 3I. This is 5I. And why is that? Because when you multiply a J, so J, I, an I is here. This was, I think, 3 minus 3I. So this was previously, I think, 3 minus 3I. When you multiply an I here, so 3I minus I squared, so 3 plus 3I. This was previously 3 plus 3I. So when you multiply an I here, this is plus 3I, and then this is minus 3. And this is 5, this is 5, and you put an I over here. And this, by the way, is minus K into H. So if you take the conjugate transpose, this is simply the negative of this one. And the eigenvalues, you can check, eigenvalues are plus 8I, and lambda 2 is equal to minus I. Again, the sum is 7I, and this would be again 7I. So before I stop, before I end this lecture, I just want to draw this table, which is actually given in your book, and just to make a comparison. So if I have real here and I have complex here, so this is field of Rn, vector space of Rn. This is the vector space of Cn. Both have n components. So nothing changes here. When I want to find the length, so the length is x norm squared. This is simply x1 squared plus xn squared. The length here is x1 absolute squared plus xn absolute squared. What about the transpose? So transpose ATIJ is AJI, where AB whole transpose is reverse, B transpose A transpose. Here AHIJ is simply A conjugate JI. So the conjugate is the only difference part here, and AB whole Hermitian is B Hermitian, A Hermitian. And then if I look at the inner product, inner product X transpose Y is X1 Y1 plus Xn Yn, and Ax transpose into Y is X transpose A transpose Y. Here the inner product is XHY, the Hermitian operator. This is X1 conjugate Y1 plus Xn conjugate Yn, and Ax Hermitian into Y, Ax Hermitian into Y is simply X Hermitian into A Hermitian into Y. This is not into Y. Okay. What about orthogonality? So orthogonality is the same definition again to cater for the conjugate complex part. So for orthogonality, you have X transpose Y equals 0. Here we have X Hermitian Y equals 0. Again, this is a scalar 0. This is not a vector. For symmetric matrix, we have A transpose equal A, and A can be written as Q lambda Q transpose, where this lambda is real. Same is the case here. AH equals A, where A is equal to unitary lambda U transpose. This is still real. Or actually, this is not U transpose. I'm sorry. This should be UH. This is UH. And finally, for the skew symmetric part, we have K transpose equals minus K. Here we have K conjugate transpose equals minus K. Again, eigenvalues here are totally purely imaginary. And finally, for orthogonal matrices and unitary, we have Q transpose Q equals I, or Q transpose equals Q inverse, or QX transpose into QY equals X. The lengths are preserved, the inner products are preserved, and the lengths are also preserved. Same is the case here. The only difference is we have unitary matrices. U is equal to I, or UH is equal to U inverse. UX into H into UY equals XH into Y, and UX norm is X norm, and nothing has changed as far as the length is concerned. So this is all we want to do from regarding complex matrices. So the thing is, instead of the Hermitian matrix, we have the instead of the symmetric matrix, we have the Hermitian matrix, and instead of the orthogonal matrix, we have the unitary matrix. So the next article is on similarity transformation, and once we do similarity transformation, then we can move on and see what happens if we don't have the full set of eigenvectors. So we'll look at the Schur's lemma, and then we are going to go and do the Jordan form. This is all I want to do from this lecture. If you have questions, we can either discuss it on Mondays or Wednesdays, or you can send me an email. Thank you.